Let's recreate the THX Deep Note in Max MSP. The THX Deep Note is probably something you have heard at the beginning or sometimes after certain movies, a very characteristic sound that's been associated now, well, with THX. It is in fact just a swarm of sounds. I believe those are cello samples sliding all the way up to this beautiful empty power chord. In this video, I'm going to show you how to recreate this in Max MSP by using a bunch of beautiful and interesting multi-channel objects. The material for this tutorial actually came from the website earslap.com, or specifically an article on that website called Recreating the THX Deep Note. You can see some trivia that it is created by Dr. James Andy Moore in the year 1982. It's been played a lot, and you can see how many lines were used, which kind of signal processor was used. But more importantly, in this article, you can see how to recreate this using code, more specifically using Super Collider code. What I wanted to do was to take the Super Collider code and take this article and turn it into a way that can be applicable to Max MSP, especially in terms of using multi-channel objects. In any case, if you are comfortable with text-based programming languages or if you're comfortable with Super Collider, do check out this article and see if you can add up onto what I am about to create. And if not, no problem, you can just see how this sound can be created and designed by using Max MSP and multi-channel tools, which again is a wonderful introduction to the world of multi-channel sound design in Max MSP. Let's see how we can do this. Here is my plan. I want to generate two kinds of sounds. I want to first generate that random, swarmy, soundscapey sound, and then I also want to generate that deep power chord-like sound that we are going to arrive at the end of that deep note glissando. And for both of these, I'm going to be using a sawtooth oscillator. The only thing is, I need to use multi-channel objects because there are a lot of oscillators at play and I cannot just create 50 instances of saw and try to control each of them individually. I mean, I can do that, that is possible, but it is too much work for no reason when the multi-channel equivalent exists. So let's do a very quick refresher on multi-channel signals. Now, before doing anything multi-channel, I just want to set up a playback system that uses a sawtooth oscillator. Saw tilde is going to generate the waveform. I'm going to put this through, let's say, a live.gain, so I can control the volume of the final output. I'm going to put that result through limmy with the argument 2, so a 2-channel limiter, just in case if I do something down the line that might blow my speakers and or my ears off. And the final result is going to go into easy DAC. Fairly standard, very standard stuff. Now, how this saw works, it can either accept a argument for frequency, and it of course sounds horrible, or with or without having a argument to determine its frequency, it can receive a signal or a float number in its first inlet that will determine the frequency. Right, so I can use a, let's say, a float number box, and I can do this. Or if I'm going to change the frequency very rapidly and I want to avoid pops and clicks and I want to do some audio signal processing or just signal processing on the frequency data, I can use sig tilde to convert this float number into an audio signal containing that same value, which would then go into saw. So this is functionally the same thing, but it is going to be preferred by us. Now, again, I do not want to create 20 or 30 or 40 or 50 instances of this. And I'm going to be using, exactly for that reason, multi-channel objects. And to turn most, not all, but most MSP objects into multi-channel objects, I can just type mc dot the name of the object, mc.saw. You can see that the patch cord has a different color. It's a bit thicker. It's carrying some thick audio signals right there. I can also do the same thing to sig. It can become mc.sig. Live.gain might become mc.live.gain. Right, and I can even actually delete all of these guys. Then the result of mc live gain can go into mc.limmy tilde. Now I do not need an argument because this is multi-channel. I do not need to define how many channels limmy needs to possess, and then the result can go into mc.easyDAC. All right, so how do we know, or how does the algorithm know the amount of channels in these multi-channel signals? By default, they are 1, and they are determined either by the input to these multi-channel objects or by an argument or an attribute, an attribute given to the initial multi-channel object. So if I tell mc.sig at chance, let's say 50, and if I turn this on, mc.sig is going to send a 50-channel multi-channel signal. So mc.saw is going to interpret all of these values as frequencies. It's going to send out the audio. MC live gain is going to gain scale those as it sees fit and necessary. And then it goes into MC Limmy and it goes out. The only problem is that I do not have 50 individual speakers to play these 50 individual channels. So it's best to just collapse these down to a stereo, so a 2-channel audio signal. And it is possible to do this by using, let's see, mc.stereo, right? Or its cousin, mc.mixdown. So both of these are going to work in a similar way, but I can tell MC Mixdown to how many channels to collapse the incoming multi-channel signal into. With MC Stereo, it's always by default 2, so I do prefer MC Mixdown. I can also give it the attribute auto gain 1 to make sure the overall gain is scaled by the number of output channels, since they're all going to be playing at the same time, and we might have to gain scale those guys. So if I put this right after MC Mixdown, well, look at what happens. The result is a 2-channel multi-channel signal, and then only that is gain scaled by MC Live Gain, and we have those 2 channels limited in case there's some clipping, and that is played through our speakers. Okay, so this is going to be our starting point. Now let's think about how this random cloud is generated. Well, I do know that I'm going to need 50 channels, and these all need to have so 50 channels and random frequencies between 200 and 400. Right, so it is not 200 to 400, it's just each channel has a random frequency between 200 and 400. And again, I can try to type this manually, or I can try to generate a bunch of random values at once, but there is a very easy way of doing this with MC objects. If I look at MC.sig, if I look at its reference, I can see that it will accept a message called deviate. Right? And if I look at the description or the explanation here, it says the message deviate will generate a random value for each channel around a center value. An optional number after the center value specifies upper range size, yada yada yada. Example, deviate 100, cutoff 1000 will generate random values for the cutoff attributes of the objects in the wrapper centered around 1000 Hz, so between 900 and 1100 Hz. Now, we don't need the cutoff attribute. We are not trying to set any attributes, but I can type a message like deviate 100, 300. And what this means when it is sent to mc.sig is I'm asking this object, mc.sig, to generate random values for each channel, which will deviate around 300 by a value of 100. So 300 plus minus 100, aka random values between 200 and 400. We can view this without playing any audio. There is the object jit.cellblock, which you might know from my other videos, which normally displays jitter matrices, but I don't know if this is a well-known fact or not. Multi-channel audio signals, or the values that they contain, can be displayed in a similar way. By default, right now, these all have the values of 0 because I did not send it the deviate message yet, but look what happens if I send it deviate 100, 300. I'm getting a bunch of random values after the 50th channel. The rest are 0 because they are not multi-channel signals, but I guess jit.cellblock is obliged to show everything in these pretty rectangles. Anyway, each time I click deviate, look at all these random values I'm getting, and do notice that these are always between 200 and 400, and it will always be the case no matter how many times I click this. So if I play this back, brace your ears, I'm getting a beautiful swarm of sound, a swarm of noise. It's like a bunch of bees just stuck in a warehouse or something like that. And each time I click deviate, it is slightly different. So what is happening, just recap this section, I'm generating these random values, which is then sent to mc.saw. So these are all being interpreted as sawtooth oscillators or sawtooth waveforms at that specific frequency. MC Mixdown turns this into a stereo signal, and then MC Live gain scales it. MC.limit acts as a limiter, and then through MC Easy DAC it arrives at our ears, or at least the computer's speakers if everything is configured correctly. Now this is a good starting point. But we can make this a bit more beautiful, and something we can do, something I have seen in the tutorial that I am using to adapt things into my own tutorial. A good idea is to use a low-pass filter, so I can use low-res, a resonant low-pass filter. If we very quickly look at the help file, you can see that it does make a sound, for instance. And it works in a very simple way. The first inlet is the audio signal on which we are going to apply this filter. The second inlet is the cutoff frequency, and the third inlet might determine the resonance, where 0 is a little bit sharp and 1 is as sharp as possible. These can also be given as arguments or attributes. So let's create a multi-channel version of this. Let's make it so depending on the frequency of each channel, there is a different unique cutoff point for that channel applied into our not low-res but mc.lowres object. Now I want the resonance to be same for all instances, so for all channels of my mc.lowres I will set the resonance through this attribute to 0.5, just in the middle. But I can put the multi-channel audio signal here, but maybe not after mc.mixdown, because I want to apply this individually to each of the 50 channels before I collapse it down to a stereo channel. Right? I don't need the the JIT cell block anymore, but I need something to go into this second inlet, the cutoff frequency. And what I want, and again, this is also used in the source that I'm going to be sharing in the video description, I am taking the signal containing the frequency values, I am multiplying them by 8, so mc dot multiplication tilde 8. Right, so now each frequency has its value multiplied by 8, and I believe that would be about 3 octaves, right? Times 2 is 1 octave, that times 2, so 4 times is 2 octaves, and that times 2, so times 8 is 3 octaves. And that goes into the second inlet, so each channel has a different cutoff point for this low-pass filter. And we can see how that sounds. Now, I don't know if this sounds different to you or not, but we can quickly check it with this. This was our original sound. As you can see, it's really harsh, and this is the version with the low-pass filter. It's much more soft, I think much more tolerable, and has a slightly different effect of this swarm, this wall of sound with random frequencies. Which is nice, but we can go further in crafting this swarm of sound, or starting point for the Deep Note. Something else we can do is to add a bit of a wobble to all of these frequencies. Right now they are very flat, each frequency is not changing, but we can make each frequency go up and down a bit. The fancy way of describing this is, of course, vibrato. We are trying to apply vibrato to each instance of our multi-channel oscillator. And how we are going to do this is essentially through adding an oscillating offset to each of our 50 channels, so that it goes up and down around a certain point, which is the frequency for that specific channel. Now, when we do vibrato in, let's say, synth design or any kind of dealings with oscillators, it might be tempting to use an oscillator, right? I can use cycle, for instance. I can type cycle 2 and then use live.scope to visualize it. And we can add this kind of vibrato to the frequency, right? We can give this as an offset frequency and it's going to create a very predictable vibrato. But with this sound, I want it to be unpredictable. I want the generated values or the generated vibrato to be random so that there is no predictability in the sound. So it's truly a swarm of sound that is randomly wobbling around, that has a random vibrato around it that can never be predicted. Now, I believe I've said the word predictability enough times already in this video, so I'm just going to introduce you to the object that makes this possible, which is called rand tilde, and it is described as a band-limited random signal. What does that mean? Well, let's look at the help file. And there it's described a bit better. So use the rand object to generate a signal consisting of random values between -1 and 1. This is noise, right? We can generate white noise by using noise. What is the catch? The catch is that these values are generated at a frequency specified by its input. Just like an oscillator, we can give rand a frequency in which to generate these random values between -1 and 1. And if we give it 400 as the frequency, for instance, it is going to sound like this. A long time ago in my videos where I was recreating the NES sound chip, I actually used this for generating pitched noise. But what if we use this as a LFO, as a low frequency oscillator? So if I set the frequency to 1, look what happens. There are random changes. In fact, each second we are getting a random value between -1 and 1, and we are interpolating linearly between those values in the course of that second, right? So each second, 1, 2, 3, 4, 5, 6, and so on, we are getting a different value, and this is completely random, or as random as it can be in the world of a computer and a digital system. So why don't we use this? Why don't we create rand and then give as an argument, I don't know, 0.5. So let's make it fairly slow, and let's see how it looks on live.scope. And you will realize, yeah, this does look really nice. So every 2 seconds we are getting a different value. Maybe let's make it 1 instead of 2. I changed my mind. And you will notice that the changes between these random values are fairly harsh because this is linear interpolation, and then there is a sharp change when one random value is done and we are starting towards the next random value over the course of our frequency. We can come up with certain algorithms to deal with this, but I'm just going to be using the simplest way, which is slide tilde, which is going to filter a signal logarithmically. For its slide up and slide down values, these are supposed to be in samples. I'm going to give it, I don't know, 40 thousandths each. Let's see if that's too much or too little. Nope, seems to be just right. Now look at this. Look at how smooth the resulting random values are, because we are sliding those values instead of these sharp edges as we go from one random form to the other. This looks like, indeed, it is just sliding from one random value to the other, giving us a continuous line. Now all I have to do is to use MC_rand instead of rand. So MC.rand. These all are going to have the same frequency, so all instances of MC.rand are going to have the same frequency, but we can give it the attribute chance50 to make sure the generation is 50 channel, so it's a 50 channel multi-channel signal. Then I can turn slide into MC.slide, and unfortunately there is no MC.live.scope as of yet, but if you really want to visualize this, I can use MC.scope. And as you can see, it looks, I mean, the frame rate is 1, but you can see that each channel has a different random value. So this is a way we can add random values or a random offset to our frequencies. However, our adventure with this noise is not over yet. Before we apply this, we have to think of a certain problem that are going to cause 2 more problems, which is going to result in 2 more solutions. The problem is thus. Frequencies are logarithmic, or at least they are perceived logarithmically by our human ears or human brains. If you are not a human, or if you have received a very specific kind of brain damage maybe to process audio linearly instead of logarithmically, I think that would be really interesting. But I'm going to assume that you are neurotypical, or at least your ears work logarithmically, so you are picking up the frequencies and they are going to work logarithmically for you. And what does that mean? What does it mean for our perception to be logarithmic? It means that each time we double a frequency, we are going to have the feeling of an octave. We are going to feel like the frequency is not only doubled, but also it is the same thing, but one thing higher. So when we go from 100 to 200, we feel like it's an octave. But if we go from, I don't know, 800 to 1600, we feel like it's the same distance, but just on a higher pitch. This means that if we give an offset to a lower frequency, it is going to be felt much more strongly than giving an offset to a higher frequency, which is going to be felt as a lesser change, even if we are changing those frequencies by the same scalar. So between -1 and 1, or between -5 and +5, or between -10 and 10, these are going to have different effects on different registers, or different octaves, or different ranges of frequencies. So we should make it so that all of these frequencies that we are feeding into our oscillator, well, the lower ones should have well, not such a strong offset in terms of vibrato, and the higher frequencies should vibrate in a larger range. Should vibrate in a larger range. Like, let's say, I'm just saying this off the top of my head, so I'm making this up. If our frequency is 200, it should have an oscillation ±20, but if we are at the frequency of 400, it should be ±50, so that it's kind of evened out. We can try to go the full way, and we can try to calculate the exact right kind of vibrato offset we can add to these frequencies. I don't find it necessary. Now, how can we do this? Well, I can change each of these values of the resulting randomized sample values, right? As in, MC rand is giving me values between -1 and +1, and I can make this unique for each channel. I can multiply the resulting -1 to +1 value with a scalar, like, let's say, multiply it by 5, so I get -5 to +5, or I multiply it by 10, I get -10 to +10 in the generated random values, which I then apply as an offset to that specific frequency. So let's do this from low to high. I'm going to create again an mc.sig tilde with the attribute chance 50. I am not going to use the deviate message this time, however. I'm going to use another message called increment, and it is described as thus. The increment message generates a range of increasing values for each channel. The range starts at the second argument and increments each channel's value by the first argument. Meaning, if I write or type increment 1, 1, well, it is going to start at 1, and each channel is going to have 1 added to it. So if I bring up JIT.cell block to visualize the resulting multi-channel audio signal, here we go. The first channel has the value 1, then 2, then 3, then 4, then 5, and this goes all the way up to 50. So the 50th channel is going to also carry the value 50 inside it. Now, knowing this, I can scale these values, right? I can use mc.scale tilde, and I can say, all right, the incoming values are between 1 and 50. These are going to be low to high frequencies. So in terms of the range of random values generated for my vibrato, let's make it, I don't know, let's make it 5 to 20, right? So the lower frequencies are going to oscillate by a factor of 5, -5 to 5, but the higher frequencies, it might go all the way up to -20 to +20, and anything in between is going to be scaled like that. The result I can then multiply with the result of my random oscillator. So I can use mc.multiplication tilde, and I can just plug these MC signals here. And as you can see, the image has immediately changed. Looks like a beautiful chaotic image, by the way. We might use this in some other video for some audio or oscillation visualization goodness. But for now, let's bring up JIT.cell block again. Let's look at this again. And now look at all of these random values that are being generated, right? And you can see, for instance, that the first horizontal line, well, they're going from -2, minus something to +1, +2. They might go all the way up to +5. But if I look at the later audio channels, the later multi-channel components, well, they are going up and down to a higher or lower amount. It's going to -4, -5. This can go up to +7, and this might go all the way up to 20 because of the way that I have set up this system. Okay, now this is one part of the solution. The second problem I'm going to have if I'm working in this way is the fact that my frequencies are random. I'm using deviate, meaning that each channel is getting a random value between 200 and 400. So the first channel may be a low frequency, it might be a high frequency, it might be a middle frequency, we do not know. Unfortunately, as far as I know, there is no way to just quickly sort a multi-channel signal. So we have to approach this in a clever way. And what I'm going to do then is this. I'm going to first stop processing audio just in case I mess something up as I'm doing this. And then I'm going to take the multi-channel signal. I'm going to turn it into a good old list, a message box containing a bunch of frequencies. And then I'm going to sort these, and then I'm going to pack these back into a multi-channel signal. How am I going to do this? So how am I going to turn audio signals into lists? I can use mc.snapshot for this. Snapshot. Now you might know that snapshot is going to take an audio signal and it's going to turn its value into a float number when it either receives a bank or upon certain intervals as defined by an argument. I want to generate the values just each time I send a bank. I do not need this to happen at a certain rate or an interval. And I can use print, not print, but print to look at the result. So let's go to the Max console, bring this back here. If I send a bank here, well, it's a bunch of zeros. Why? Well, of course, because I turn off the audio context, and maybe I should not have done that, because for audio signals and MSP objects to work, I need to have the audio on. If I do this now, well, look at this. It's just giving me each of these channels in a certain order. So from 1 to channel 50, I'm getting the values of each channel. I just need to collect all of these together into a pretty list. And I can do this by using zl.group. This object is going to store and output a list. And if this receives the output of MC snapshot, each element is going to be added to a list, and when ZL group receives a bank, it is going to send everything that it contains as a single list. So then I need a very specific order of events. When I press this button, I need a bank to go into MC.snapshot. I need all 50 values to be sent to ZL group, and once that is done, I want to send ZL group a bank so that its output is sent. Instead of doing this manually, I will just type in TBB into a new object box. T is short for trigger. This object is going to trigger certain events, messages, symbols, even lists upon receiving a certain kind of input. How it is set up right now is going to make it so that the rightmost outlet is going to happen first. So the bank, that is what the B is short for, is going to go into MC snapshot. Everything goes into ZL.group. And once that is done, then the first outlet, so my second bank, is going to be sent to ZL.group. And let's see. Bam, there we go. Now we have a list containing all the frequencies. This might look like just a mess of numbers. Maybe we are going into the matrix. I don't know, but these are the frequencies that we want. But these are not sorted yet. And we can sort these by using, well, you guessed it, zl.sort, which is going to take a list and is going to sort things in a alphanumeric order. So again, if I bang this, well, look at this. It starts from 20, and this will be the case no matter how many times I click deviate to generate new frequencies and then send a bank. The lowest one is going to be the first one, and the highest one is going to be the last one. All right, well, this is a list. How do we turn this back into that sweet, sweet MC signal? I can use mc.list tilde. I need to tell mc.list tilde with an attribute, chance 50. Yeah, it does say bad number in the console, but this is how it works, so we do not need the console anymore. I I'm going to send mc.list with the attribute chance 10 this list, and then once it's sent there, it will just be turned into a multi-channel signal where each channel contains that element in the incoming list. And that we can send into mc.saw and mc.multiplication. So this should sound the exact same. Yep, this is our nightmare swarm, all right. But now I can go further with this. I can, instead of just sending these directly to mc.saw, I can take my vibrato setup here, and I can add the result of that by using mc.plus tilde to the signal containing the frequency values for each channel. So adding an offset generated by rand, and then the result goes into both the oscillator and also mc.multiplication. So frequency, added offset, that is our vibrato, and the result is vocalized. Let's see how this sounds. Okay, maybe I can make the oscillation much stronger, so 25 to 50. And maybe you can hear it. Maybe you can hear that each oscillator in the swarm is slightly vibrating, is slightly oscillating. Again, just for the sake of comparison, without vibrato and with vibrato. You can probably hear that it really fills out the sound. It makes it, I don't know, to me it feels like it makes it more humane. In any case, it sounds cool, and that's what we want. And this is the first part of this tutorial, right? Not the first part of this video. We are going to continue. You can look at the play bar if you don't believe me. But this is the first part of what we want to accomplish. This is our starting point. All right, so now we need to create the end sound. And what is the end sound? Well, the end sound is the MIDI note 14.5, I believe, spread as a power chord, meaning, you know, fifth, octave, etc. But instead, maybe we don't do it as a power chord because we are already using sawtooth oscillators, so the sound is going to be pretty fat. We are just going to use MIDI note 14.5 as the root note of our final deep note chord, and then we are going to add I don't know, 6 or 7 octaves, I don't know. All right, so we're going to create some kind of our multi-channel signal where the frequencies are the MIDI note 14.5 in, you know, for terms of frequency, not MIDI numbers, and then octaves of that, right? So maybe each 5 channels or each 6 channels, we are going to have an octave higher, and then an octave higher, and then an octave higher. So it's going to be this really high, fat, beautiful sound. Now, the question is, how are we going to create this? Because this might be a bit tricky to create with deviate. It might be possible to create with increment, but it might be a bit tricky as well. And I want to introduce you into another way of generating these kinds of series of frequencies or MIDI notes or any number sequence. And for this, we are going to use Uzi. More specifically, Uzi 15. You can see it's a very dangerous object. The first outlet says, watch out. Because when you send a bang to Uzi, it is going to send out the amount of bangs equivalent to its first argument. So Uzi 50, when it receives a bang, is just going to send 50 bangs. Look at this. If I type in print here, go to the Max console, boom, 50 bangs immediately, or as fast as the computer can do it. This is a Max MSP analog to for loops in text-based programming, if you're comfortable with that. But what I'm interested in is the third outlet, the current index, because when I send a bang to Uzi, I'm just going to get the sequence of numbers that go from 1 to 50. And maybe I can manipulate the sequence of numbers that is generated. So instead of getting 1 to 50, I just get 14.5, 14.5, 14.5, 14.5, 14.5, and then an octave higher, and then that happens for 5 or 6 more times, and then an octave higher, and so on. And then I take all of these into a list, and these are the frequencies that I want to generate. Now let's think what kind of math visitor we can use for this. I'm going to start by dividing these values into 7. Why 7? Because 7 is a great number. And what happens if I do this? Well, I'm going to get 0.14 something something something, and 0.2, 0.4, 0.5, and so on and so on. 1 point something, 1 point something, 1 point something, 2 point something, 2 point something, 2 point something, 3, and so on. Right, so maybe I can get rid of the fractal components of all of these values, so I just get a bunch of zeros, and then a bunch of 1s, and then a bunch of 2s, and then a bunch of 3s. And how can I get rid of the fractal component? Well, I just remove this dot. Normally what would be a mistake is actually a positive for me, because now the calculation isn't with floating point numbers, but instead they're all forcibly turned into integer numbers. So if I do this, I get 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, 2, 2, 3, 3, 3, 3, 3, 3, 3. So I get 6 zeros, 7 1s, 7 2s, 7 3s, 7 4s, 7 5s, 7 6s, I believe, and then 2 7s. Sure, why not? Okay, so how are we going to turn these into 14.5 and octaves thereof? Well, I can multiply these by 12, right? I'm thinking in terms of MIDI notes or semitones, and if I do this, and I'm just going to get 0, 12, 24, 36, 48, 60, 72, and 84. So I'm going to get 0, an octave, 2 octaves, 3 octaves, etc. Meaning I can just add to whatever that value is, I can add 14.5 to that. So if it's 0, it's just 14.5, the MIDI note 14.5. If it is 12, it is 14.5 plus an octave. If it's 24, it's 14.5 plus 2 octaves, and so on and so on. And lastly, because I'm going to be working with frequencies, I can use M2F, MIDI to frequency, to take the MIDI number and turn it to a frequency. And there we go. I have all the frequencies I need for my multi-channel signal containing the frequencies of the deep note chord that I will be using as the endpoint of this slide from a swarm of noise into this beautiful chord. So then I just need to use the same trick I have used at the beginning with ZL group and ZL sort, not really necessary here, and mc.list to turn this into a multi-channel signal. So ZL.group, right? So it is accumulating these frequencies as a list. Luckily, the second outlet of Uzi is going to send a bank once all of the bangs are sent. So once all 50 bangs or 50 values are sent, we are going to get a final bang from here, which can go to ZL group to trigger the list output. Okay, so here are my frequencies. They are already ordered, so I can simply use mc.list attribute chance 50. This can go in here, and then the result is going to be, we can confirm this with a jit.cell block. The result is going to be, boom, the frequencies that we need. Fantastic, look at this. These are the frequencies of the deep note chord, or my approximation thereof. So what if I plug these into my oscillator and my low pass filter? So instead of the swarm sound, I'm going to be plugging these guys in. And let's see if it sounds good or bad or something in middle. Okay, not bad. A bit too computer soundy, a bit too static. It can be a bit annoying if you just listen to this for a few minutes, but luckily this is THX Deep Note, meaning that we are supposed to listen to this for a few seconds. However, there is a trick that can turn this from this very flat sawtooth sound into something a bit more fat, and something sounds like a bunch of cellos or a nice church organ. And that is, you might have guessed it, it is vibratos, adding a bit of a wobble on each frequency. And luckily we have already created that algorithm that generates those specific values that we need. So I can just copy my vibrato system. Right, for this I want a smaller, more subtle wobble. or more so subtle offset in vibration, offset in frequency, but otherwise this should stay the same. Maybe the frequency of the random value generations can be, instead of 1, it can be 0.6, I don't know. I just have to click increment here, and when I have my frequencies as a multi-channel signal, just like before, I can use mc.plus to add the offset on top of the frequencies. Then the result goes into the oscillators, or the oscillator and the low-pass filter. Okay, so let's hear it. Ah, beautiful. You should be able to hear this difference. It sounds a bit more reverby, a bit more fat, a bit more full, because each oscillator is vibrating at a different speed to a different, arrival point of oscillation, because all of these oscillations are random. So we are getting this beautiful fat sound. Maybe a bit more wobble could be interesting. No, that's a bit too much. Maybe 2 to 7? That might be nice. Perfect. Now again, without the vibrato. And with the vibrato. It's really unbelievable what just a bit of vibrato can do to a sound. It makes it much more beautiful, especially in a multi-channel context. Okay, so we have our start and end points to create the THX Deep Note. Now, the only problem is interpolation, and this is both a bit tricky and not as tricky as you might think. It is tricky because, as far as I know, there is no interpolation object for audio signals in Max MSP. There are ways, we are going to do it in a few seconds, but there is no, I don't know, interp tilde. As far as I know, it would have been pretty weird if this did end up being an object, but in this time, in this version of Max, this is not an object. However, linear interpolation is indeed what I need. I have these two audio signals containing frequencies here, and I want to morph one into the other. If I can do that, then I'm going to have the beautiful result that I want. Luckily, there is a way of interpolating between audio signals, and that is through the magic of Gen tilde, which is going to create native audio signal processing routines, aka all of those really cool Gen patches that you might or might not know. If I lock the patch or unlock the patch and hold Command on my keyboard and double click on Gen, you'll see that I have my sub patch right here. I'm not going to use the default objects in this Gen sub patch, but instead I'm going to do it like this. I'm going to use the mix object. Mix is a linear crossfade of inputs. It's going to interpolate between two audio signals by an interpolation factor. The first inlet is the output if interpolation is 0, that's our first input. Then the second inlet is output if interpolation is 1, that's our second input. And then the third inlet is the interpolation factor, which should be between 0 and 1. And we want this to be a dynamic parameter, so I'm going to type param into a new object box. I'm going to declare a parameter. I'm going to give it a name. Let's call it THX slides, THX mix, THX mix, and I can give it a default value of 0. And that can go into here, and whatever the result is going to go to out1, so it's going to be the output of this Gen patch. So for instance, if I type sig tilde and then 5 as an argument, so an audio signal containing 5, and then an audio signal containing minus 2.22. What is the output going to be? If I type a number tilde to visualize the results, well, by default, I'm going to get 5, but I can now, when my patch is unlocked, right click on the first inlet, choose THX mix, and I can change this value. And you can see as I go from 0 to 1, the value is linearly crossfading into minus 2.2. I can go further. I can go to higher values than 1 and to lower values than 0, and this interpolation is going to adjust accordingly. But for the purposes of what I'm doing here, this is not necessary. So this is the system I'm going to use. And let me turn off my audio context first, because I'm going to talk about a delicate matter and I do not want my audio context to hear it. From my experience, MC Gen, so the multi-channel counterpart to Gen, is a bit capricious. It's a bit mean. It might crash on you. It might not only crash on you, but it might delete the contents of the MC.gen subpatch. I'm saying this because this has happened to me a few times. I even had situations that right before a concert, my reverb MC Gen subpatch was gone, so I had to recreate it over the course of 20 minutes while sweating bullets. And I do not want this to happen. I believe this is a bug, of course. This is a bug that will hopefully be fixed, maybe even by the time you're watching this video, or you're watching this video many years into the future and you are playing around with max 12 instead of max 8. Doesn't matter. But what I like to do is, if I convert something into MC.gen, and you can see the inside is still the same, MC Gen and Gen will have the same objects and the same parameters and the same logic of working. In any case, I like to keep a copy of it that is not connected to anything in my patch. And then I would like to duplicate this. So if something goes wrong with my MC Gen patch, I have a copy of it right here. Now you might say, but you can save the MC Gen patch as a separate file. Even that file sometimes gets deleted. It is very frustrating. So just to be safe, and I don't think it's going to happen in this video, it's good to have a copy of your MC Gen patch stashed away somewhere, not connected to anything. Alright, so our MC Gen patch is still here. I have the frequencies of the noise swarm going into the first inlet, and the second inlet is going to receive the ANT goal, the frequencies containing the THX Deep Note chord, and the result of this mix is going to go into our sawtooth oscillator and the low pass filter. I'm again going to right click on the first inlet and choose THX mix, and let's see if this is going to work. Going from 0 beautiful. Here you have it. The THX Deep Note recreated in all of its glory in Max MSP. To make this a bit more beautiful, let's just add a, I don't know, live.slider into the mix. And go into the inspector, I don't know, give it the long name of THX slide and the short name of THX slide. Let's make this go from 0 to 1. Let's make the unit style float. And let's make it, I don't know, let's make its orientation horizontal instead of vertical. So this is going to send out values between 0 and 1. So we can say THX mix $1, and this can go into or MC Gen. Oh wait, I did it wrong. It should be like this: THX mix $1. There we go. Beautiful. And there is one more thing we can do to make this really accurate, really beautiful, and that is to make sure the highest frequency in a random cloud goes to the lowest possible frequency in the Deep Note chord. And the lowest frequency in the Deep Note, the noise swarm, goes to the highest frequency in our Deep Note chord. By doing this, we can, well, make things much more interesting and more beautiful sounding. And we can do it like thus. Okay, so let's do ZL group, right? So we have our list, and this will be from low to high, right? This is the list containing the frequencies of the Deep Note chord, and I can just use ZL.rev to reverse the list. So now the first element is going to be the highest frequency and the last element is going to be the lowest frequency. So when converted to multi-channel signals, the first channel is going to be the highest and the second and the last channel is going to be the lowest frequency. And if I just do this, it should sound a bit nicer. Beautiful. And to make sure that our scaled values are, appropriate, instead of scaling the random values between 2 and 7, let's just do 7 and 2 instead, right? MC scale 1 to 50, the incoming channel indices. They are scaled not from 2 to 7, but from 7 to 2. So we are reversing this scale as well. So one more time for good measure. Let's hear that beautiful THX slide. Fantastic. So to sum all of these up, yeah, it is a bit challenging to design sounds and design these chords using multi-channel objects, but in a way it's easy as well. It can be intuitive if you learn how these works, if you're comfortable with multi-channel objects, multi-channel oscillators, generating random individual values for the multi-channel components. These are gateways to really creative and interesting sound design. You can use this as the starting point for other applications. Instead of creating a THX Deep Note, you can create different chords, or you can interpolate between different chords. You can generate different kinds of noise swarms and do all kinds of cool things with it. I hope you have been inspired by this video, and again, thank you for watching.